All right, 2 minutes. 2 minutes. Yeah, it's gonna be a light class today. All right, let's get started. It's 12:30. Lord, thank you for bringing us together this afternoon. Thank you for all the blessings that you've given us in our lives. I pray that you would continue to bless us, continue to give us what we need. Help us today, Lord, to have ears to hear, eyes to see what's necessary for us. In your name we pray. Amen. Okay, so what are we doing? What are we doing today? So just had our quiz. Quizzes are in process of being graded, right? I had a general backlog of grading due to an exam that I had to grade last week, and now your guys' quiz. So um, that'll be done in the next couple days. Grades will be posted. Just so you guys are aware, the quiz grade will be based off of question one, right, which was worth 15 points, and the rest of the exam grade is based off of the final three questions that are on there, right? Just because I combined all the points together, so that's how it's going to distribute in your guys' grading system, right? We're gonna go over. There's nothing from last class. All right, these things are due, right? So our next assignments are due on November 1st. So you've got a couple weeks, right, to get this done. That's where that's where we'll be at. Today we're gonna resume. We're gonna review exam one. Then we're gonna start topic 4. All right, so we're into rigid body kinematics today. Right? We'll talk about that. Right? So here it is. Right, question 1. A volleyball player serves the ball with an initial velocity of v naught, which we know is at 20 degrees. It has a magnitude of 13.4 meters per second. We want to determine, first of all, will the ball clear the top of the net? And second of all, how far is it going to land? Right? How far from the net will it land, right? So not the total distance, but this distance. I'll call that X, right? I want to know what that distance is, the chunk from the net, right? So it's whatever the total distance is minus 9 meters. right? So how do we do this, right? So it's a projectile motion problem, and because it's a projectile motion problem, we know we can use our pre-canned kinematic equations, right? So for part A, the first thing we want to do is we want to find the time that it takes to reach x is equal to 9 meters, right? So I'm trying to figure out, right? I'm trying to figure out how high the ball is when it reaches the net, right? What else happens when the ball reaches the net? Well, we'll have to have traveled 9 meters in the x direction, right? So the amount of time that it takes it to go 9 meters is the amount of time it's going to take it to travel to be at the net, and I need to figure out how high it is, right? Hopefully it's more than 2.43 meters, otherwise it doesn't clear the net, and then the second part of the problem becomes trivial, right? Because it's just, well, it lands at 0 from the net, right? Because it hit the net. I understand that it doesn't perfectly drop, right? But that's how we would handle that. So does it clear, right? So we need the time that it takes. Well, we have an equation, right? X is equal to x naught plus v naught in the x direction times time plus 1/2 a in the x direction t squared. The way we do projectile motion problems, we assume that this x direction acceleration is 0, right? And we're also told that that's traveling with a constant velocity, I believe, right? No, we said it's an initial velocity. It doesn't matter, right? We're saying the acceleration is 0 in the x direction. Right? We always assume that it's 0 in the x direction for these problems. We're also going to start at 0, right? So we end up with 9 is equal, well, v naught in the x direction, if we look at our triangle, right, v naught x is equal to v naught cosine of 20 degrees, and v naught y would be v naught sine of 20 degrees. So sine 20 degrees times time. Right, so this becomes 9 is equal to 13.4 times the cosine of 20 degrees times time. I can solve for the time and I'll get 0.715 seconds. That's 0.715 seconds. So it takes less than 1 second for the ball to reach the net. Right, so that's the first part of part A. Now we need to use our y direction equation. Right, and what we do is we're going to evaluate this equation at 0.715 seconds. What do we know? Well, we know that we start at 2.1, right? I'm sorry, we're looking for y. So y has to be equal to my initial height, which was 2.1 meters, plus 13.4 times the sine of 20 degrees, times 0.715, which is my time, minus 1/2 times 9.81. Why is it 1/2? Well, because the acceleration, or why is it minus? Because the acceleration is negative, right? Acceleration is negative. It's 0.715 squared. And this will tell us that we get 2.87-ish meters, depending on how many decimal places you carried, right? 2.87 meters is larger than 2.43 meters, so we clear the net. So we clear the net. I better give myself enough slides for this. So we clear the net. Part A done. So what do we have to do for part B, right? Part B asks us, I'll get there. how long it takes, well, it doesn't ask how long, it asks us to figure out how far this goes with respect to the net, right? So we need to figure out how long it takes us to get to the end point, right? Well, that's when y is equal to 0. So we want to figure out how long does it take me to get a y distance of 0 meters if I'm measuring from the ground, right? Okay, let's do that. And use the same equation, right? So here's my y equation. Right? There it is again. It's the same equation. We're just going to end up putting some different things in here. So what do we want? Well, we know that our final distance is 0. We know our initial was 2.1. We know that v naught y is going to be v naught sine of 20 degrees. So that's 13.4 times the sine of 20 degrees times time minus 1/2 9.81 times time squared. We use the quadratic formula to solve this for time, and we'll get 1.31 seconds or negative 0.374 seconds, right? And so get rid of that one. We get rid of that one. It's not 0. We just get rid of that one because, right, I made a lot of time travel jokes about why we get rid of that one. And this makes sense, right? Because you would expect for it to take longer for it to reach the ground than it would to hit the net, right? Because they happen sequentially, right? So it should be longer. Could you have done this at, like, broken it down and started it at the net, right? Yeah, you could have, but then you would have had to figure out what the velocity is at the net, right? Which you could do from the kinematic equation. It's just more work, but you can totally break it up in more spots, right? So I got this. Now I need my x direction equation again, right? Because I've got x is equal to x naught plus v naught x times time plus 1/2 ax t squared, right? I'm going to evaluate this at 1.3 seconds. So what do I know about this? Well, x naught is still 0, right? I'm going to measure this from where the person is serving. Okay, what's v naught? V naught in the x direction is v naught times cosine of 20, right? This is still 0. Ax is still going to be 0. We're going to assume that it's 0 here still. So x is equal to v naught x times time. X has to be equal to 13.4 is the cosine of 20 degrees times 1.31 seconds. So x is roughly 16.5 meters, right? And this is the total distance, not the x that I drew on the picture, right? So x from the net is 16.5 minus 9, which gives me 7.5 meters. Right, so I land 7.5 meters. Now, I'm not an expert on volleyball court size, so I don't know if that's in or out of bounds, right? Well, that's what it means. Okay. So that's problem 1. You guys have any questions on problem 1? No? Okay. That brings us to question 2, right? Your grandma sweetly asks you to figure out, yeah. Good enough. Thank you. It was an ace. It was an ace. Getting those hard-hitting facts today. Thank you, Mauricio. All right, so it's Easter time, right? And you're sitting at your dining room table, and your grandma sits next to you, and she wants you to figure out what's really important in life, right? Which is the acceleration of blocks A and B, right, and the tension in the cables. Right, so we're asked We're asked to find the accelerations of block A and B. So that's two things, right? That's an acceleration. We also need to know the tension in the cable, right? And there's two tensions here, right? There's two tensions. There's the tension in the cable connecting A, right? There's this tension here, but there's also this tension here. There's a tension on block A, but there's a separate tension on block B. Well, what do we need to do here? Well, since we're asked for accelerations and forces, we're going to use Newton's second law, right? That's right off the bat. That should have been our giveaway. And if we're using Newton's second law, then I better draw my free body diagrams, right? So I've got my weight, I've got a normal force, and I've got some tension, right? I'm going to put my coordinate system in this direction. I'm going to draw my kinetic diagram, which is just going to have mass times the acceleration of A. It's not going to, there's going to be no acceleration upwards off of the plane, right? It's just going to be in line with the plane. And I forgot one thing here, right? We'll try to draw it right there. This is 30 degrees, right? That's 30 degrees. That angle. Which means that this angle up here is also 30 degrees. Block B is a little bit easier, right? We have our coordinate system as such. Here's block B. Right, I've got the weight of B. I should really label this one the weight of A. There's no normal force, but there is this tension. I'll call this TB and TA, right? And then my kinetic diagram for this. I'm going to assume that this is positive. M, B, A, B. This should also be MA. Yeah. Okay. So I'm going to assume that that's positive. What? Because I don't know how. I don't know right off out. There exists conditions where the block could be heavy enough to pull block A up the hill, right? But there also exist conditions where block A would be heavy enough to pull it down, right? And so we're just going to assume positive if we don't know. Okay? We're just going to assume positive if we don't know. And then our math will tell us if we got it right or not. There's also one other thing, we'll get there in a second, right? So there's one more free body diagram, right? We've got this pulley. And this pulley has the tension of A on one side and the tension of B on the other. And we're actually told a bunch about this, right? We're told that it is a massless, frictionless pulley. So if you were to draw a kinetic diagram for this, it would just equal 0. Why? Because there's no mass there. Right? It doesn't have a weight. There's no mass. Right? So the inertial term is 0. But this couples the two systems together and gives us an expression for our tensions, right, in terms of each other. Now, when we're looking at this, right, I don't know the weight of A. Well, I know the weight of A. Sorry, let me start over. I don't know the tension of A. I don't know the tension of B. I don't know the acceleration of A, nor do I know the acceleration of B. And so that's 4 things. So if I sum the forces on these 3 free body diagrams, I get 3 usable equations. So I'm going to need a 4th equation here. And we'll talk about that in a second. But let's start with what we have here. Okay? If we look at block A, okay, I'm going to sum my forces in the x direction. And that's going to be equal to M, A, sub A. Well, all I have here is my tension minus the x component of my weight, which is the weight sine 30 degrees. And that's equal to MA, AA. I'm going to leave this as equation 1. I'm not going to plug anything in yet. For block B, I'm going to sum the forces in the y direction. Right? Summing the forces in the y direction, I will get the weight. I'm sorry, let's start that over. The tension of B minus the weight of B is equal to the mass of B times AB. And that's equation 2. And then for the pulley, we use green, which will not. For the pulley, if I sum my forces in the y direction, right, that's equal to 0 because the pulley has no mass, right? Mass times acceleration is 0. This is 2ta minus tb, or 2ta is equal to tb. Call that 3. Right, and so when we look at this, right, I've got an unknown here and here, AA and TA, AB and TB. So I've got 4 and I have 3 equations. I need one more. Where am I going to get an equation from? Right, well, go back to the schematic here. This is connected by a cable, right? This is connected by cable. And we did a problem just like this in class a few weeks ago, except it was flat, right? Right. I can define the lengths of this cable segment, right, to be this. Because remember, if I add up all the segments, I get a constant length, right? Kind of like your shoelaces. Doesn't matter how I position it, right? There's only one length of shoelace. There's only one length of cable. Right? So I can create an equation where XA plus 2XB is equal to some constant. Right? So our cable kinematics come into play here. We'll do it on the next slide. Cable kinematics. XA plus 2XB is equal to some constant. And I'll take the derivative of this with respect to time. The velocity of A plus twice the velocity of B is equal to 0. I'll do it one more time, right? Take the time derivative again. AA plus 2AB is equal to 0. Now I have a relationship between AA and AB. So AA is equal to negative 2AB. We'll call that 4, right? So let's regroup our equations and plug some things in, right? So I'll take equation 1, which I had on the previous slide. Right, this is going to become TA minus 200 sine of 30 degrees is equal to 200 over 32.2, right? That's the mass, times A sub x. TB minus 350 is equal to 350 over 32.2 times AB. Instead of calling that AX, we'll call this AA, because that's what it is. My pulley equation tells me 2 times TA is equal to TB. And the last equation I just wrote tells me this. So, just to highlight this, right? I've underlined these, right? I've got a system of 4 coupled equations, right? And I'm going to have to solve these 4 equations simultaneously. And so I'm going to solve these simultaneously. In doing so, you get 152.7 pounds. What's up? Yeah, what's up, bro?
Sorry, am I going back? I didn't get all the information.
Mm-hmm. There you go. No problem.
So I heard a rumor of the third and fourth staff dressing up for Halloween.
Yeah. Yeah. It's not a rumor. It's going to happen. That brings a good point, Brandon. For participation next week on Friday, you guys need to come in costume. That's what the participation activity is. Doesn't have to be an elaborate costume, just a costume. At the end of class, we'll do a fun activity that's not dynamics related. Okay. Friday's class. The one closest to Halloween.
Are we going to magically disappear?
No. No. There have been cases of people magically disappearing on campus, though, and they get vanished to the GCU hotel. I have heard. Right. All right. You guys have any questions so far? Right. Let's take a stop here for a second and ask that. Everybody following? Everybody doing it? Okay. So these are our equations, right? We can solve them. When we solve them, I want to have them color coded. 304.35 pounds, right? The acceleration of A is 8.4 feet per second squared. And the acceleration of B comes out as negative 4.2 feet per second squared. So I chose wrong, right? That's what this is telling me. I chose it positive, but it's going to be negative. It's going to be pointed downward. How would you know that that makes sense? Well, I mean, it's 150 pounds heavier than the block on the plane, so you would imagine that it would effectively pull it down, right? Especially if there's no friction, right? If there was friction, it's a different story, but if there's no friction, then it's not a problem. Okay. So if you solve those out, right? So you're gonna have to do a double substitution, right? Plug this in to the first equation, plug this in. Where is it? So if you plug this into the first equation, then you can solve TA in terms of AB, right? Then you can plug all that into here and solve for TB, right? You're gonna have to substitute all the way down and solve them individually, or if you're comfortable using the solver in your calculator, you can do that. Right? But you can always brute force it. It's important to remember that when we're doing dynamics problems, the tension in the cables doesn't have to be the same, right? Because this is not in static equilibrium, so the tension on each one is going to be different because there is motion involved. Right? That's why the tension in A is not equal to the tension in B. Right? In fact, it's twice, right? It does boil down to statics a little bit. In real life, pulleys are not massless or frictionless, right? So this is not, it's a decent approximation because they're very light compared to the rest of our system, so we neglect them typically. And we'll typically have really nice bearings on them that make them spin almost as if they are frictionless, right? But we're always losing a little bit. But because it's not statics, right, you can't just say that the tension here is equal to the weight, right? Where is it? Where's my pointer? Somewhere. I had it before. There it is. Right? Can't just say that the tension is equal to the weight. This obeys a static equilibrium. This does not, and this does not, right? Because it's moving. You guys have any questions on that one? No, not yet. All right, so then there's this guy, and this is the exact problem that we did in class. It's just asking you for a slightly different set of answers, right? So in class, when we did this, we needed to find VA, VB, and the distance. I think this distance A, right? Is that correct? Something. We need to find something different. This time when we're doing it, we need to find the length of this line and the initial velocity, right? Those are the two things that we need. In order to get there, we're gonna have to find some other things as well. Okay, so what do we know? Right, if I look at this diagram, right, I know that this is going to travel some distance. Let's just call this x before it breaks. This I was told was 3.5 meters per second, right? This was also 3.5 meters per second. D was given as 0.09 meters, right? 9 centimeters. I converted it to meters because everything else is in meters, and at the end I'll convert my final length back to centimeters, right? Because I can. We're told that V sub C is 6.0 meters per second, right? And this is all stuff that we're just pulling right out of here. Right? I guess B wasn't known. A was known. And here. We're going to be looking for V naught and this distance here, L. Remember, when we did this before, these red arrows that I'm putting on here, right? These were given to us by something we call VREL, right? That's our relative velocity of the ball as it's spinning. So there are a few things that we need to do here, right? We're asked for a distance and we're asked for a velocity. So we're not asked for force. So Newton's law is gone, right? We're not asked for forces. There's nothing in here about accelerations. We're going to ignore Newton's law. So if we remember from class, we end up needing both momentum and energy for this, right? How would we know that from the problem statement? Well, you know that from the problem statement because you're asked to find a distance. The way that we find a distance is we have to use energy, right? Energy is going to give us, work energy is going to give us a distance. And we're asked to find velocities, right, which is also an energy and a momentum thing, right? If we're looking at this diagram, we don't know VB, we don't know V naught, we don't know L, and we don't know this velocity, right? So that's 4 things on here that we don't know. We're asked to find 2, but there's a total of 4 that we don't know. And we're going to end up needing 4 equations because we do have 4 unknowns in our system. Okay, so how do we go about this, right? How do we start this? How do we start? Well, I'm going to start with my linear momentum equations. And I get 2 linear momentum equations, right? I get an x direction and a y direction, okay? If we go back and we look at this, we're talking about just the translational momentum, the linear momentum. So VREL is only a rotational velocity, right? VREL describes how we are rotating. So we don't use that to describe our translation. We're going to use V naught. And V naught moves to the right, and so the total momentum here at the beginning is 3 times m, because those 3 masses are all moving with V naught, right? 3 times m times V naught. So that's my initial momentum here in the x direction. My initial momentum in the y direction is 0, right? It's not moving in the y direction. It's going to move in a straight line. So we can start our x direction equation here where we'll have 3 times m times v naught. When we get to the next part, all 3 balls are no longer spinning, but they are all moving translationally. A and B are moving in the j direction or the y direction, right? C is the only one that's moving in the x direction. So it's the only one that's going to have momentum in the x direction, and that will be m times vc, right? Well, I can get rid of that. So this is just 3 V naught is equal to VC. VC was given to us as 6, right? 2 meters per second in the I direction. So linear momentum already gave us the answer to part A of the problem. Right? Part A was find V naught. Done. So we're going to have to keep going, right? So in the Y direction, we talked about this in the Y direction. We've got 0 initial. We've got the mass times the velocity of A, right, minus the mass times the velocity of B, right? Because one's going upward, one's going downward. Those are my Y directions, right? And some interesting stuff happens here too, because then we see that VA is equal to VB, but VA is equal to 3.5 meters per second in the J. So both of these are 3.5. So we've eliminated 2 of our unknowns with our first 2 equations, right? We've solved for VB and for V naught, but we still need to get L, right? We still need to get L, so we're not done here yet. But this is important, right? This is going to be useful for the rest. So where do our other 2 equations come from, right? We said that this is going to be an impulse momentum and a work energy problem, right? And we were specifically told that this system is frictionless. So that should cue us in to let us know that it is specifically a conservation of energy problem. Right? Specifically, we're using conservation of energy here. But we're going to keep with momentum right now. We're going to use our angular momentum. Specifically, I want you guys to look at this. Remember, when we're talking about momentum, we need to pick it about a point, right? We have to measure angular momentum about a specific point in space. And I'm going to use this starting point, G, right? I'm going to use G as my place where I'm going to be measuring this. About G. So if we look back right at our diagram, what's my angular momentum about point G initially? Well, I've got 3 masses that are equal. My angular momentum is just my linear momentum, m times v, times the perpendicular distance I am away from wherever I'm rotated, right? In that case, these are all at L, right? So this is m times v times L. Well, the v is that relative velocity, right? That's what's driving this rotation. So we're starting with 3 times m times v relative times L. And then we need the angular momentum about that point G of A, B, and C, right? A, B, and C. So if point A is some distance x from G, right? That's my perpendicular distance. That's going to cause, right, if we look at our standard coordinate system here, right, that uses a positive rotation counterclockwise. Well, VA is going to be positive, right? It's m times v sub a times x. V sub b goes the other way. It's going to create a clockwise rotation. So that's going to be minus v m times v sub b, sorry, times x plus a, times x plus a. Why? Because it's the distance of x plus a away from G. And finally, C is also going to be a negative, right? Because it's going to cause a clockwise rotation. This will be m times vc times d, because that is the distance that it is away. All right, so let's write all that down. M times VA times X minus M times VB times X plus A minus m times vc times d. I can get rid of all my masses, right? Because if I divide through by m, cancel. So this gives me 3 v rel times L is equal to VA sub X. Remember, VB is equal to VA, right? All right, so these two are going to go away because they're the same. And so I can plug in some numbers, right? I'll get 3 times V rel times the length is equal to negative 3.5 times 0.16, because that distance A was given, times 6.0 times 0.09. And I have to leave that because I don't know these two things. I don't know them. So in order for me to solve for L, I need to solve for the relative velocity that these things are traveling at. So that brings us to our final equation, right? Our conservation of energy equation. Now, let's go back to our diagram for a second. Do I have enough slides for this? That's another question. I might need one more. There we go. Right. So we're looking at our diagram here, right? I need to do energy. Energy is the last thing that can help me. Conservation of energy in specific, because we're told this is a frictionless system. There's no losses. Is there any change in potential energy here? Is this moving in a gravitational field, right? We're told that this is on a horizontal table, right? We're looking top down at it. So if it's on the table, is it going to be changing height? No, right? So there's no potential energy for gravitation. There's no springs in here that I see, bless you. So there's no potential energy due to elasticity. So it's just a kinetic energy problem, right? Now, we have to remember when we're dealing with energy, the thing that's important is it's a scalar. So we can add all different types of mechanical energy together, whether they're rotational or translational, right? And that's the key here. This first state at the beginning, right? So the kinetic energy at the beginning has to equal the kinetic energy of all the particles after, right? So what do we have here? Well, we've got translational kinetic energy, 1/2 mv naught squared. And we also have, or 1/2 3 times v naught squared, right? Because there's 3 masses. 1/2 times 3 times m times v naught squared. What about this? We've got rotational kinetic energy as well. That's 1/2 times j, right, times omega squared. Right, I didn't give us what j was here, right, but when we did it in class, right, we knew for a point mass that it's ml squared. So what are we doing? Let's talk. Let's write it down. Let's write down what we have so far. So my kinetic energy, and so conservation of energy. So we've got 1/2 times 3 times m times v naught squared, right? My translational kinetic energy. Why is it 3? We've got 3 masses that are identical, right? So that's that. We also have 1/2 times j times 3 times j, which is m times r squared, times v rel over r squared. Those go away. In the second part of this, we don't have any rotational kinetic energy. It's all translational. So we have 1/2 m VA squared plus 1/2 M VB squared plus 1/2 M BC squared. Once again, all of my M's cancel, and I get left with 3/2 V naught squared plus V relative squared is equal to VA squared plus 1/2 VC squared. Why is it VA squared? Well, I have 1/2 of VA plus 1/2 of VA, right? So 1/2 plus 1/2 is 1. 2/2. So I can plug everything that I know into here, right? So I'll get 3/2 times 2 squared plus V rel squared is equal to 3.5 squared plus 1/2 6 squared. And I can solve this for V rel. And V relative ends up being 4.02 meters per second. And I'm going to take that and I'm going to put it back into my other equation, right? So my previous equation for angular momentum told me that 3 times V rel times L is equal to negative 3.5 times 0.16 minus 6 times 0.09, right? So I'm going to plug my V rel into there. So L has to be equal to negative 3.5 times 0.16 minus 6 times 0.09 divided by 3 times 4.02, right? I'll just taken my V rel, divided it out, right? Which gives me an L is equal to 0.091 meters, but I was specifically told to give it in centimeters. It's 1.1 centimeters. Yeah, it's the same one that we did in class, just asking for slightly different things. That's 2 problems that we did that were ones from class, right? You guys have any questions on this one? No?
So what was the velocity?
The horizontal for V naught, so it was 2. And that came out, Zach, when we did our linear momentum in the x direction up here, right? Because we only have, we're looking at the linear momentum, we only have 2 things that are traveling purely in the x direction. There's V naught and there's C, right? So we end up with 3 times M times V naught is equal to M VC. We can cancel our M's, right? And we're just left with 3 V naught is equal to C. So VC being 6 divided by 30 is 2. Any other questions? So we can do this, right? Part A. So there's one more question. And this one, we'll talk about it in a second. You guys have any more questions on this one? No? All right, so here's the last one, right? You've got a car coming off of a car hauler, right? The guy who's unloading them did a great job of taking the first 2 off and putting them in park without the brake on, right? So I guess putting them in neutral. And then the last one just kind of gets away from him, comes down and bumps car. So car A hits car B, that hits car C, and then to add insult to injury, car A hits car B one more time, right? Because why not? All right, so 3 identical cars are being unloaded from an automobile carrier. B and C have just been on the, yeah, we went through this. Right, all right, so here's the information we're giving. We know the velocity of car B after the collision with car A is 5.04 feet per second. After the second collision, when it hits car C, it slows down to 0.63. And then after it gets hit by car A again, it gets boosted to 0.709 feet per second. So we know all of the velocities of car B, right? We know it starts at rest. So it's 0 to start with, then it increases to 5.04, then it decreases to 0.63, then it increases to 0.709. That's, we know everything about car B that we need. We're also told that these are 3 identical cars. Well, I don't think they're identical. One's yellow, one's blue, and one's red, but I mean, I get it. They're identical. So that's a big clue to tell you what, that the masses of these are the same, right? The masses of these are the same. So we need to find the final velocities of car A and car C, right? So we need to find the final velocity of the lead and the rear car. And we want to find the coefficients of restitution for all of our collisions. Okay, so let's talk about that first, right? Coefficient of restitution was the very last equation on the equation sheet. All right, it's right there. E is equal to V prime A minus V prime B over VB minus VA. And we'll talk about it a little more in a sec. So what do we do? Right, we're talking about collisions, and what was the number one thing that I wanted you to remember about collisions? These are impulse momentum problems. Always and forever, just use impulse and momentum to talk about collisions, right? So we're going to use impulse and momentum. First one is we'll talk about the collision of A into B. So I'm going to draw a highly realistic car here. There it is. Hold your applause, please. Thank you. All right. So here's car A at the beginning. So what are we doing? Impulse momentum. We need an impulse momentum diagram. So the initial momentum plus my impulses has to equal my final momentum, right? Okay. So the initial momentum of car A is going to be MA times VA, right? The initial momentum of car B is 0 because it starts at rest. It's not traveling at all. So it has no momentum to start with. My impact causes an impulse force, right? But they're equal and opposite on each of the cars. So they're going to cancel out as well. So my initial momentum is just this. This has to then equal the momentum, call this MB VB, and MAVA prime. Now, is that really MA and MB? I wrote that there, but really we remember they're identical. So MA is equal to MB is equal to MC, right? They're all the same. If you write it like this, though, somebody could tell you, hey, they're not actually all the same. One of them was a minivan, right, and therefore was a far superior vehicle and weighed more, right? And one was a tractor trailer, right, and was really large, right? So we can play around with it if we leave it like this, but we know they're going to cancel anyway in a second, right? So let's look at this, right? We'll write our equation. Our initial momentum, MAVA, is equal to try that again, MAVA prime plus MBVB, right? Conservation of momentum for this one. Well, the M's all cancel, right? So we're left with V sub A is equal to VA prime plus VB. Well, we know all of these, right? We were told that the car originally starts with 5.76 feet per second. That's going to equal VA plus, well, VB after the first collision, we were told that VB was what? It's 5.04, right? Feet per second. So we can solve this for VA prime. VA prime is equal to 0.72 feet per second. Right, 0.72 feet per second. Great. That's not the final velocity of car A, but this is going to help us because why? Because we need the coefficient of restitution here, right? And coefficient of restitution tells us that E is equal to VA prime minus VB prime over VB minus VA. Well, in this case, what do we have? Well, VA prime was 0.72. VB prime is actually what we're calling VB, which was 5.04, right? Remember, the primes in this one are telling us this is the after state and this is the before state, right? These are the velocities before collision. These are the velocities after collision. VB before collision was 0. VA before the collision was 5.76. If you do this, you get a coefficient of restitution of 0.75. The coefficient of restitution of 0.75. What happens if you messed it up and you flip these, right? Well, you have, what would your coefficient of restitution be? It would be 1 over 0.75, right? It would be 1.3. Can you have a coefficient of restitution of 1.3? What does coefficient of restitution tell us? It tells us the amount of energy that's transferred during our collision, right? Can you have more than 100% of your energy transferred? No, right? So if we've gotten something over 1, that should be a big red flag that something went wrong somewhere, and we should look at it again and make sure that we have the right values where they need to be. And so that's A into B. This now becomes a rinse and repeat problem, right? We're going to do B into C and then A into B, right? A into B again. All right, so let's do B into C. So there's B. Once again, we're going to get these things here, right? We're going to get MBVB, MBVB prime, and MCVC. Okay. We write our equations, MBVB equal to MBVB prime plus MCVC, right? We can plug in the things that we know, right? So we know I messed this up. I know VB, right? This is 5.04. That's going to equal VB prime, which we also know because we're told what it is, which is 0.63, plus VC prime. We solve this. VC prime is, or I guess VC in this case, it doesn't really matter. There's only one. VC comes out as 4.41 feet per second. So this is one of our answers. This is the final velocity of C. Right? This is the final velocity of C. We need the coefficient of restitution. Right? In this case, it's going to be VB double prime. Sorry, I don't know why I use double prime. It's not appropriate. VB prime minus VC over VC initial minus V, right? 0.63 minus 5 points, no, minus 4 point, oh, what am I looking at? Minus 4.41 over 0 minus point, minus 5.04, right? I'll re-crunch this just really quick. Also 0.75. Right? Then we'll do A to B sequel, right? This time it's personal. I guess A wants revenge on B for hitting B in the first place. I don't know. I don't know why it's personal. No, it's not pretty. Okay, so what do? Okay, rinse and repeat again, right? This time, both of these have an initial velocity, so they have an initial momentum, right? MAVA prime, MBVB prime, MAVA double prime, MBVB double prime. Okay? We know everything about B once again. We can write our equations, right? We'll get MVA prime plus MVB prime is equal to MVA double prime plus MVB double prime, right? We'll cancel our masses. We'll plug in the things that we know. Well, VA prime was 0.72 plus VB prime was 0.63 is equal to VA double prime plus 0.709. All those are given. All right, so VA double prime is equal to 0.641 feet per second. We can plug this in here, right? This is going to tell us VA double prime minus VB double prime divided by VB prime minus VA prime 0.641 minus 0.709 divided by 0.63 minus 0.72 is equal to 0.75. Okay. So we just needed to essentially do the same problem 3 times. Okay. Man. You guys have any questions?
I don't even, I guess I thought of, I guess sort of not working everything, but I guess I thought we were supposed to do something like that, V squared.
So yeah, so that's the kinetic energy, right? Could you use kinetic energy to do this problem? No, because you can't account for the dissipation of the energy due to the collision based on what we have, right? The problem with using work energy for collisions is that a collision is going to create energy, well, not create energy, but it's going to transform that mechanical energy into sound and heat, right? So it's not a conservative process, right? Which is why we use momentum and impulse for it. So you could do it as work energy, right? But you're going to experience losses, right? And you can't, so you can do it as work energy, but you can't do it as conservation of energy, right? We don't know enough about the work that's done by one car on the other to do this as a work energy. You guys have any other questions? Okay. Well, in that case, let's talk about some topic 4 stuff. We're going to talk about the kinematics of rigid bodies. So the time has come. We are no longer talking about particles, but systems of particles, right? And remember, I want you to, well, not systems of particles, rigid bodies, right? I want you to think of a rigid body as a system of particles that is constrained to move together, right? This is a system of particles, right? This is like, I joke around with some classes that I don't believe in atoms, right? But atoms are just a system of particles, right? That whole thing that are held together, right, by atomic bonds, okay? Molecules, things like that, right? But think about this table. This table is a collection of particles, right? But if you move one of those particles, the whole table is going to move, right? And we can talk about how this table moves by characterizing how the center of gravity of the table moves, right? So when we're done, we want to be able to analyze rigid body motion about a fixed axis, planar translation of a rigid body, and analyze general plane motion of a rigid body. Okay. So what is a rigid body? Right? It's a solid body in which the deformation is zero or so small that it can be neglected. Right? A solid body that when I push on it, the deformation is so small that it can be neglected. I have deformed this table somewhere, right? But nobody can tell because the table barely deformed. It's on the nanometer level. The distance between any 2 points on a rigid body will remain constant regardless of the external forces exerted on it. Now that's true to a point. You guys get to materials, you'll learn from Dr. Wright that sometimes if you exert too much force on something, it will bend, right? Or it will deform. So assuming that we haven't reached a yield strength, right? If we push on a solid body, it won't, the 2 points on it will stay the same length, right? We're going to assume a continuous distribution of mass, right? So we're going to assume that, if I cut this table in half of the mass of the table will be on one side and half will be on the other, right? It's continuously distributed. Each section has some piece of mass associated with it, right? So it's no longer just saying, hey, take this table, condense it down to a single point where everything's acting on it. This thing has mass as we go, right? It has mass as we go. When we talk about kinematics, right, we need to remember that we are talking about the geometry of motion, right? So this is just like kinematics that we've talked about before, except that instead of tracking a point, we're tracking how an entire rigid body moves, right? This is going to give us the relationship between time and position, velocity, and acceleration of all of the particles forming our rigid bodies. To do this in translation, we use the same equations that we use for a point. Okay. For translation, look, we've got rectilinear or curvilinear translation. We're also going to talk about rotation about a fixed axis and general plane motion. And general plane motion is just what we talk about when we have an object that is both rotating and translating at the same time. When something is rotating and translating at the same time. So we look here, the linkage here between these two train wheels. That's an example of curvilinear translation. The link stays horizontal as it swings, right? But it follows this curved path. It's also general plane motion, right? Because it is doing this motion, but it's also moving down the track, right? So it's rotating and it is translating. How do we determine the velocity at the tip of a turbine blade? This one seems like it might be a good thing for us to know, right? Because we have vertical axis wind turbine projects that we're doing. Right, we'll talk about that in a little bit. And finally, planetary gear systems are used to get high reduction ratios with minimum weight and space. So how do we design the correct gear ratios, right? Well, we need to know how much power we need to transmit. talk about translation. Translation is going to be pretty straightforward. So you will notice that, I apologize, I should have brought this picture to the front. At 25 is the slide number. It has nothing to do, it's not like labeled or anything. I just didn't bring it to front. I apologize. Doesn't cover anything important. You'll notice that a lot of the diagrams that we're going to use to illustrate these things look like potatoes from here on out. That's like general 3-dimension. You just have some like potato, right? Some potato shaped thing. All right, so let's look at our potato here, right? So consider my rigid body and it's translating in space, right? So that means that if I pick any point on this potato, it should be traveling, right? We're talking about just translation, right? This is not rotating at the same time. You've perfectly knuckleballed this potato and it just stays like this and it flies through the air like on this path, right? And so these, no matter if it's this path, that path, right? Whatever path I want to take this on, those 2 points are always going to be traveling on the same path, just parallel to one another, right? These 2 points will always be this distance away from each other. So if we differentiate their position with respect to time, well, we get this, right? And so another way of thinking about this is I can talk about the velocity of each of these points, right? Or the position of each of these points, right? Or I can talk about the relative position between those 2 points, right? So how do I get from A to B? How do I get from B to A? Okay. Remember, relative position is just, if we're saying RB is equal to RA plus R of B with respect to A. So R of B with respect to A is just equal to what? Well, it's equal to RB minus RA, right? So if I take the time derivative of this, notice this distance will never change, right? Because it is a rigid body. So because the relative position never changes, if I take the time derivative of it, it's 0. So I'm left with this. So all of the particles on this potato have the same velocity, right? And if I take the time derivative of this equation a second time, the same thing happens. So all the particles have the same acceleration. So for translation, if we're translating, every single particle will be moving with the same velocity and acceleration. Not true when we start talking about things that rotate, right? Because the further away I get from my center of rotation, the faster I will be spinning, right? The faster I will seem to be spinning for the same angular velocity. The tangential velocity will be different. But for translation, right, this is all going at the same speed. It's all going at the same acceleration. And because of that, we can define our, they're not open. Yeah. So before we go there. So because of this, the same kinematic equations that we have been using still play for translation over rigid body. Right, so you can still use the x is equal to x naught plus v naught t plus 1/2 at squared. Because in order for us to define the translation, we only need to know how one particle on the rigid body moves. Right, that's all we need to know. If it's purely translating, doesn't matter which point you pick, they'll all be translating in the same direction. All right, so let's talk about rotation about a fixed axis, or RAFA, right? RAFA is rotation about a fixed axis. And specifically, let's talk about velocity, right? So imagine for a second, I got my potato's back, right? And this time we're rotating this potato about some fixed axis that we call AA prime. So imagine, right, I've got this axis through my potato, right? And I'm going to rotate around it like this, right? With some omega. Omega is going to be our angular velocity. Right, so I've got some omega here. Right? So I want to figure out what the tangential velocity of my potato is, right? It turns out that I can do this at any point outside of here, but how do I do it, right? So the velocity vector is dr dt. And it's tangent to the path, and it has a magnitude of v is equal to ds dt. So we can derive this, right? Here's the punchline. The tangential velocity, the velocity of some particle at any point on my rigid body, is equal to dr dt, which is just omega cross r, right? So we're going to need cross products. We're going to need cross products. And we'll do an example later where we're hopefully refresh cross products, right? But you guys are feeling rusty on cross products, break out your notes, come to office hours, do what you need to do, right? Omega cross r. V is equal to omega cross r. If we have a two-dimensional problem, right, instead of a 3D one, this breaks down to V is equal to omega times r. Okay? So, what is the direction of the velocity at point A if I have an angular velocity of omega? Right, so, show of hands. Right, so what is the direction of the velocity at point A? Is it to the right? Who thinks it's to the right? Who thinks it's to the left? Okay. Who thinks it's up? Okay. Who thinks it's down? It's definitely down, right? If this is rotating, right, if it's rotating this way, and if it's rotating counterclockwise, right? And we did the math, because I know you guys all did the math in your head, right? You didn't just do this by intuition and knowing that this is rotating counterclockwise, so that point should be pointing down, right? But the math backs this up, right? If I do omega cross r, right? Omega is omega, right? This is a two-dimensional problem, so this is just about the z direction, it's just in the k. So this would be omega in the k direction, omega k hat, cross negative L times I, right? So we're measuring from the center. This has to go negative L in the x or the I direction, right? And if you do the cross product, which we'll talk about, right? So remember, cross product, I've got IJK or XYZ. There's different notations that you can use. I use IJK, right? These are unit vectors. Omega is 0, 0, omega, right? Because it's only about the z-axis, it's only in the k. And then I've got negative L, 0, 0, right? There's no x and no y there. So if I do the cross product, right? And this is going to be hard for me to show you on the thing. So what do you do for a cross product? Well, you take the I column, right? And you cover it up. And you cover up the top row, right? So you're going to cover up, I'll mark it in red here. You're going to cover up these areas that are to the left of the red line and above the red line, right? And what am I left with? This. 0 times 0 in the j, right? Because this 0 in the j, minus 0. So you're going to cross these, right? So what are we left with? In the I direction, we get, I'm also going to write this up here as well. What's this? The IJK circle. Okay, let's talk about the IJK circle before we move on. I cross J gives me positive K. J cross K gives me positive I. K cross I gives me positive J. If you are doing it in this counterclockwise fashion, then you'll get a positive. If you do I cross K, you'll get negative J, right? J cross I is negative K, and so on. All the K cross J is negative I, okay? All right, so here we are, right? I've got my cross product, right? So what do? I take 0 times 0 plus 0 times omega, right? So this is just going to be 0. So in the I direction, I end up with, I'll write this down here, 0 I.
When you're on the cross like that, that's saying like 0 times omega
Yes,
L, or
yes, exactly. So when I had the cross drawn, like I did, 0 times 0 plus 0 times omega. Right? So you go, we'll do another one, right? So if we use the blue lines, right? Now we're going after the J component. Now look what I've got here. I want you to see this. If I eliminate that middle row, right, for J, imagine that that's gone, right? I'm covering up this central column, right, that central column. I'll get I cross K, right? I cross K here. That gives me what? Well, I cross K gives me negative J, okay? So then you get 0 cross 0 here, right? So come all the way down here. 0 times 0 minus L times omega, which is just 0 minus L, 0 minus negative L times omega gives me positive L times omega, right? But it's negative L omega J. Why is it negative L omega J? Because remember, I cross K gives me negative J. So this J has a negative sign associated with it. All right, so remember, it's cross minus cross. Okay? So a way of thinking. So you go cross, subtract, cross. Okay? Multiply, subtract, multiply. See, you gotta do the third one, right? 0 omega 0. Third one is we're gonna hold K, right? We're gonna cover up K. Well, that's I cross J. That gives me a positive K. Well, it doesn't matter because I've got 0 minus 0. Hey, look. Look at that. Cross products. Cross products are super useful. Cross products, if you do them correctly, you don't have to worry about, as long as you keep track of your signs and your vectors, your cross products should always give you the appropriate direction of how things are moving. All right, you guys have any more questions? All right, so intuitively though, I hope that the direction that the velocity would be on this makes sense. Right, you're spinning it this way, right? So if you're tracking this point, it's got to be moving down this way. Once it gets here, it's going to be moving that way, right? It's going to just be tangential to that circle that this is moving in, right? All right, let's talk about acceleration. So that was velocity. Now when we talk about acceleration, angular acceleration, or alpha, as we will call it, we get some fun things, right? We get the return of tangential and normal coordinates. Right? So this is the reason why we talked about this earlier, really, was to introduce it then. So what happens, right? If you break this all down and you take the derivative of the velocity with respect to time, well, that's d dt and omega across r, right? We can distribute this, right? Do the whole thing, and you'll end up with this. My acceleration is alpha cross r plus omega cross r. Okay? Alpha cross r, this is kind of like omega cross r, right? This is going to give me my tangential acceleration. The acceleration tangent to the path. This is my normal or my radial acceleration. So this is typically going to be pointed back towards the center of curvature, right? Back the radius of curvature. And this is omega cross r. Right? So you got to do two cross products here. You got to do omega cross omega, and then omega, then this cross r, right? We can kind of simplify this a little bit, right? In two dimensions, we just call this normal tangential coordinates. And you get the tangential acceleration is equal to r times alpha, and the normal acceleration is equal to r times omega squared. Similarly, in two dimensions, we get the velocity is equal to r times omega. So if we're doing a two-dimensional problem, we don't need to do the cross product, right? We can just say this, this will get us the magnitude, right? This will get us how much acceleration and how much velocity, right? And then we need to assign the direction to it based off of the right-hand rule. Okay, so if we have let's consider the motion of a representative slab, right? It's an election year, so make sure you guys vote for Representative Slab. He does good work. Awful, I can't believe I said that. All right, right, and so we're just looking at the XY plane, right? So everything here is going to rotate around the Z-axis, right? The Z-axis is coming out of the board at us, right? So everything's going to rotate around here, right? So we're just XY plane translation with a rotation about the Z, right? And because we know that this is two-dimensional motion, right, we can say, well, this is omega is just in the K, alpha is just in the K. Can you still do the cross products here? Sure. That's not an issue, right? We can still do the cross products, and the cross products will still be correct in two dimensions, but we don't need to, right? We don't need to do them. We can simplify this because everything is perpendicular to the axis of rotation. We can break this down to normal and tangential acceleration, right? If you look at this point P, it's going to have some tangential acceleration, and it's going to have some normal acceleration. And it's also going to have some tangential velocity. Okay? So, what direction is the normal acceleration of point A? We're talking about the normal acceleration of point A. Who thinks that's going to be to the right? The normal acceleration. Thinks that's going to be to the left? Who thinks it's up? And who thinks it's down? To the right. So let's go back here and look at it, right? Normal acceleration. Remember, normal acceleration is always pointed back toward the center, right? It's always pointed back toward the center. Remember, the reason it's normal and not a radial and transverse is because this is just some potato, right? Every point on that potato wants to stay together, right? So there's some acceleration pulling everything back towards the center of rotation, right? If I'm spinning in place, right? It's different if I'm gonna, throw the football, or if I hit the tether ball on the string, right? That's a little bit different. But the math, here's the math, right? The normal acceleration is negative omega squared times r, right? Well, we have omega, right? Negative omega squared times L times I. Hey, look, this gives me a positive L omega squared I. Right? Just positive x direction. Right, you guys have any questions so far? We're doing all right. All right. So the main thrust for right now is going to be doing these in two dimensions. We'll get to a couple of three-dimensional problems towards the end of the semester, specifically when we get to gyroscopic motion, like the last week and a half of the semester or last week of the semester. But the main thrust of what we're going to be doing, I will introduce it in three dimensions to give you the general, like the gist of where the math comes from. But most of the things that we're going to do are going to simplify down to 2D. Now, does that mean we're not going to do any 3D problems? No, probably do one or two here or there, but they're not going to be the main thrust of it. So what are the equations here? Well, hey, guess what? It's kinematics. So yeah, omega is d theta dt, right? So in a rotational system, theta is my displacement, omega is my velocity, alpha is my acceleration, right? We can do all these things. But if you have something that's uniformly accelerated, you can use these equations. Hey, check this out. If omega is angular velocity, isn't this just the same as this, right? It's equivalent, right? These equations, these kinematic equations are equivalent to the translational versions, right? We're just changing the variables. So now instead of x, we have theta. Now instead of omega, we have, or instead of velocity, we have omega. And instead of acceleration, we have alpha. But these are equations that we've used before, right? These are the typical kinematic equations. We have one more here for uniform rotation, where alpha is equal to 0. Right? We get that. Well, this is just this equation with alpha equal to 0. Right? So the kinematic equations don't change, right? But the variables that we're putting to them do, right? Because now when we're talking about something that's rotating about a fixed axis, we are talking about something that is changing its angle with respect to time. It's not changing its physical position, it's changing its rotational position. Think about tetherball. I smack a tetherball around a pole, have this nice looping arc to it, right? Let's try one. So I've got a double pulley. Everybody loves a good double pulley, right? They're the best. They're twice as good as a single pulley. All right, cable C has a constant acceleration of 9 inches per second squared and an initial velocity of 12 inches per second, both directed to the right. Okay. We want to determine the number of revolutions of the pulley in 2 seconds, the velocity and the change in position of the load B after 2 seconds, and the acceleration of point D on the rim of the inner pulley, which is right at the top. So there's 3 things. How many revolutions does this thing do in 2 seconds? How far does this travel, this weight B, how far does that travel in 2 seconds? And what's the acceleration of point D, right? So let's draw a picture. Let's draw an actual picture of this. So I'll draw that inner pulley first, right? Just the inner pulley by itself. And so if I draw the inner pulley, all right, and this right here is point D. I know this is 3 inches. There's some angle, right, that this happens to be traveling through that I'll call theta. Right? It will also have some omega in that direction. Here's my coordinate axes, right? This is normal, tangential, looks like that. I have a cable coming around here, right? And that cable at point C has an acceleration of 9 inches per second and a velocity squared of 12 inches per second. Right, so 9 inches per second squared, that acceleration. Okay, so that's what we know about the inner pulley, right? I would say that when we get over to here, right, I know that this has to have 2 components. A normal and a tangential. You can't really see that well. Let's try that in a different color. I don't know if that's any better. So point D has a tangential and a normal acceleration component. How do we know that? Well, we were just talking about it, right? We're just talking about it. Any point on my rigid body has a tangential and a normal acceleration component associated with it, right? Hey, check this out. What do you guys think that the tangential acceleration of point D is? Just by looking at this, we can figure out what A dt and V sub D are. What do you guys think those two quantities are? What's A dt? Just guess, best guess. VD and A dt. Best guess. N. What do we think? We're looking at the top one. What is my acceleration tangential at point D? Answer this question. If I have a cable that's running around a pulley and I pull it, how fast, and it's connected to that pulley at that point, how fast should the pulley be moving at that point? All right, so we've got vectors there, right? How can we manipulate a vector along its line of action? No guess. No. Yeah, this is gonna be a long hour.
Would it be the same at point C? If it's the same?
Yes, it is the same at point C. Why? Because cables and vectors. I know that the cable is moving right there. It's going to move, right? The cable is accelerating by 9 inches per second squared at C. That's a vector. I can move that vector along its line of action to anywhere, right? That means that the acceleration at that point has to be equal to the acceleration of the cable. Likewise, the velocity of point D that's tangent there has to be equal to the velocity of the cable at that point. Is that always true? Yes, as long as there's no slipping. As long as the cable is not slipping on the pulley, that will be true. What if it's slipping? Then it's not true. And we'll talk about that later, but not today. Today it's true. Today it's not slipping. When I draw my outer pulley, I'll have something like this. Right? Remember, the inner pulley sits inside of the outer pulley. That's why it's the inner pulley. So we're going to start with the inner pulley here. We've got some data for the inner pulley, right? We need to find the number of revolutions that this is going to take. Remember, these things are both on the same axis of rotation, and potentially they're being driven, well, not potentially, they should be being driven by the same motor or whatever you have driving. So if the inside pulley does a certain number of revolutions, right, in radians, the outer pulley should move the same number of radians, right? So we can use our kinematic equations, right? We want to find the number of revolutions on the inner pulley. How do we do that? Well, theta of t is equal to theta naught plus omega naught t plus 1/2 alpha t squared. I'll call this equation 1. All right, I'm going to call this equation 1, but I don't know alpha, and I don't know omega naught. Right, I don't know alpha. Well, I can find omega naught. Why? Well, I know the velocity at point D, and I know the radius, right? Because remember, the velocity is equal to omega times r. So omega should be equal to the velocity divided by r. Specifically, if we use the velocity at point D, we know that our initial angular velocity, we'll call it omega naught, is 4 radians per second. This is the point in the class where you really want to make sure that your calculator is in radians whenever we're doing anything. Anytime we have a rotational problem, make sure we're in radians. Okay, make sure you're in radians. You don't want to be doing this in degrees. Similarly, I can figure out what alpha is, right? Because remember, the tangential acceleration is equal to alpha times r. Alpha is 9/3, right? Because we know a dt is 9. So this is 3 radians per second squared. So we can plug this into our equation, right? Theta of t is equal to well, we're going to assume that we start at 0. Right? So we're doing this. Well, part A asks us how many revolutions we travel in 2 seconds, right? So let's do that. How many revolutions do I have in 2 seconds? Well, we're going to evaluate this at 2 seconds, right? If I plug in 2 for t, right, theta, right, theta of 2 is equal to 4 times 2 plus 1/2 of 3 times 2 squared. And so therefore theta at 2 seconds is equal to 14 radians. Well, we specifically asked for revolutions, right? How many radians per revolution? We get 1 revolution per 2 pi radians, right? So 1 revolution is 360 degrees, right? That's what it is, 2 pi. So I'll multiply this by 1 rev for 2 pi radians. The radians cancel, and theta of 2 is 2.23 revolutions. Part A.
Is that 2 pi per pi value?
2 pi radians. Yeah. 2 pi radians. 1 revolution per 2 pi, right? So you have 1 revolution every 360 degrees. So if they're spinning around the same axis and they have the same omega and the same alpha, they have to travel through the same number of revolutions. Now the outer pulley is going to cover more distance, right? But it's going to travel through the same angle, right? But because it's larger, it'll move up. If you track the point at the top, it's going to move farther, right? But the angle do the same. The angle do the same. All right, so we can do part B now. And for part B, we're going to use, remember, part B is figuring out how high that weight gets raised, right? What is that distance that the weight travels? Okay. So for part B, we're going to use the outer pulley for this one, right? And we can figure that the velocity of B is equal to omega of t cross r, or, because this is a two-dimensional problem, omega of t times r. Now, we have a kinematic equation for the angular velocity. It's omega naught plus alpha times time. And so we can figure out what omega of t is going to be at 2 seconds, right? And we already found omega naught and alpha, right? Because we did that for the last problem. It's 4 radians per second and 3 radians per second squared. So we can find omega at 2 is equal to 4 plus 3 times 2, or 10 radians per second. Why do we care about at 2 seconds? Because we want to know how far we moved in 2 seconds, right? Why do we need omega for 2 seconds? Because we can figure out the velocity of point B, right? So the velocity of point B is going to equal what? That's going to equal 10 times 5. And that's going to be 50 inches per second upward. But how does that help us find the change in the y position, right? Well, the change in the y position is equal to the r, the radius, times the angle that we've traveled in 2 seconds. So why do we even find the velocity? Well, we need the velocity for the next part that we're going to do. We need the velocity for it. Or were we asked to find? I think we were asked to find the velocity and the position. I don't remember. But we needed it. We need it for something. We don't need it for anything that we're doing next. Or did I just find it to find it? Let's find out. Let's go back for a second. Yeah, part B. You want the velocity and the change in position of the load B. So what are we doing here? We're actually tracking the velocity at this point, right? Because cables, same reason as before. Turns out that this is going to have some velocity in this direction here, right? We can figure out the change in this distance, right? Because this x, well, x is equal to r times theta, right? Equal to r times theta, which is what we did. So that gives us part B, and then part C is to find the acceleration at point D, which we have half of it already, right? But we need to find that normal acceleration. So what's the normal acceleration? Well, based on our equations that we've defined so far, it's negative omega naught squared times r. So our normal acceleration is given thusly. So if I wanted my total acceleration given as a vector, right? The acceleration of d, that's going to be the magnitude of the acceleration of d. Well, let's not do it that way. So I have the two parts, right? If I wanted to leave this as a vector, I'd have a tangential component and a normal component, and I'd leave it, right? The other way that we can talk about this is in terms of a magnitude and an angle, right? Because if I know how long it is and at what angle it's at, I know everything I need to know about how to place my vector, right? So how do I get the magnitude? The magnitude of a sub d is the square root of the normal component squared plus the tangential component squared, right? Because remember, this is just a right triangle, right? So we're looking for the hypotenuse. This is just Pythagorean theorem, which tells me that it's 48 squared, square root of 48 squared plus 9 squared, which is 48.8 inches per second squared. I want the angle. Let's call this phi. Tan of phi is equal to my normal divided by my tangential, which is negative 48 over 9, which is 79.4 degrees. Okay, so let's look at this for a second, right? I've got here, this is my tangential, this is my normal. What I'm looking for here is the resultant of these two, right? The hypotenuse of this, of said triangle. And this is a sub d, right? And this is phi. in that top corner. And if that's phi, then this angle is also phi. So we have to do some trig. Right? We've got to do some trig to get everything where it should be. All right. If the homework asks you for it, do it this way. If you were on a quiz and you got this question and you left it as here's my normal component and here's my tangential component, I'm fine with that. But specifically, if the homework asks you for the acceleration vector, they're probably going to want this format where you give them the angle and you give them the magnitude. You guys have any questions on this? No? Okay. So let's look at this one. I've got a conveyor belt, a series of small machine components being moved by a conveyor belt. It passes over a 6-inch radius idler pulley. At the instant shown, the velocity of point A is 15 inches per second to the left, and its acceleration is 9 inches per second squared to the right. Oh man, velocity is going one way, and acceleration is going the other way. We need to find the angular velocity and angular acceleration of the pulley and the total acceleration of the machine components at point B. All right. So let's draw it. Let's draw it up. I'm going to draw the pulley. So my pulley, here's point B. It's a 6-inch radius. I was told that the velocity at point B is this way, right? And I was told that the acceleration is in the opposite direction. And we know that if we're talking about something that's rotating, that we should be prepared to have our normal. Because of the way this is set up, we know omega is going to be this way and alpha is going to be this way. How do we know that? That's an excellent question. Remember, what contributes to the angular velocity? Well, that's the tangential velocity, right? The tangential velocity is going to the left. If I have my circle here and I'm pushing it here, it's going to rotate this way, right? It's going to have an angular velocity that's counterclockwise. But if I'm accelerating, the tangential acceleration controls my angular acceleration, right? The equation for tangential acceleration is alpha cross r, or alpha times r, right, in 2D. And so if I'm accelerating the opposite way, alpha's got to be going in the opposite way as well. Right. We're told that VA is equal to negative 15 inches per second, right? And why is it negative? Because it's in the opposite direction. A sub A is equal to 9 inches per second squared, right? Okay. So I know VA and I know AA. what is the velocity at B and the acceleration at B? That conveyor belt is a rigid conveyor belt, right? Rigid. No change in size. It's inextensible, right? It's inextensible. It's not able to be compressed or expanded. So with that being the case, what is the velocity of B and acceleration at B? How does that belt transfer that velocity and that acceleration? Another way of thinking about it. What's the velocity of the belt at point B if it has, at this instant, a velocity of 15 inches per second to the left at point A? If I throw this 15 inches per second at this point, right? Well, that's a bad example. It's not rigidly tight. Oh, so if I pull on a rope, okay, pull on a rope. If I pull on a rope, say this is just like a cable or belt, something, right? It's a belt. It's going to be a belt. Pull on the belt, okay, and you take a picture, and I'm pulling with a velocity v sub a at point A. What should the velocity of B be if it's a rigid body? The same, right? It's the same as last time, right? So if at this instant in time, one point of this rigid body is translating with a specific velocity and acceleration, and all points on that rigid body have to be translating by the same velocity and acceleration, right? And if I pull the table, right? If I pull the table with a constant velocity, the entire table moves, not just part of it, right? So point B, so the velocity here is also equal to the velocity of B, is also equal to the acceleration of B tangential. Make this red so that matches vision. So for part A of this problem, we need to figure out omega and alpha. That is what we were asked to find. How do we find omega and alpha? Well, if the velocity is omega times r, then omega is equal to 1 over r times the velocity, right? We know the velocity at point B, right? So omega is equal to 1/6 times 15 is equal to 2.5 radians per second counterclockwise. Similarly, we know alpha, right? We know that the tangential acceleration has to be equal to alpha times r. So alpha is equal to 1 over r times a t. Alpha is equal to 1/6 times 9. And this is going to be equal to negative 1.5 rads per second squared, because we know, based on the geometry, that this has to be moving, this has to be accelerating counterclockwise or clockwise. Now here's the thing with an idler pulley, right? What is an idler pulley doing? It's slowing down the line, right? Slowing down the line. So the acceleration is going to be opposite of the velocity, right? Because that just indicates to us that we are decelerating. Right, so it's slowing down. Omega is slowing as we pass through there, right? We're going to idle. There, we got part A done, right? Part B is defined. Part B is defined the total acceleration at point B, right? We'll do that on the next slide. Oh, currently, there we go. B, find A sub B. Well, what do I know? I already know that A sub B of t is 9 inches per second squared. AB normal is r omega squared based off of our equations that we developed earlier. So we can plug those in. We'll get 37.5 inches per second squared. Remember, it wants the magnitude, right? So for the magnitude, we've got AB tangential squared plus AB normal squared. It's equal to the square root of 9 squared plus 37.5 squared. Which gives me 38.6 inches per second squared. And I can find my angle, which is going to be the tan inverse of my normal over my tangential. Which gives me 76.5 degrees. So if this is my idler pulley, and this right here is point B, my acceleration, that's not a good one, it looks like my acceleration vector would look like that. Just like that. So what's this saying? Well, this is saying that as this thing passes the top of point B, right? As my crate of components passes over the top of this idler pulley, the acceleration is upward, right? Up and to the right. Well, think about it, right? It's traveling on that conveyor. At the top point is where it's still gonna be traveling in that direction, right? And as we come down, it'll still go to the right. It'll just flatten out. For problems like these, we didn't really use any kinematic equations very much, right? What we used were the relationships between acceleration, linear acceleration, and rotational acceleration. Right, so keep that in mind. You guys have any questions on this?
At the beginning, where you said at point A, I was confused on when it says that there's a velocity to the left and acceleration to the right.
So here we have, so we're told that this is moving to the left with the velocity to the left and acceleration to the right, right? So physically what this means for us is that this is going to be slowing down as it reaches this pulley. Right? The idler pulley is made to slow down this, right? To slow this system down. Now this is an instantaneous velocity, right? It says at the instant shown, this is the velocity at A. So if you took a snapshot in time, right? If this happens to be the case, then every point along this belt has to have the same velocity and acceleration, which is how we get the acceleration and velocity at point B. Right? It's weird a little bit, right? But think about this. If you've ever been at the shopping mall, right, and you're going on the escalator, well, I guess anywhere with an escalator, I always think of the mall because it's product of a misspent youth, I suppose. But if you're ever at the shopping mall, next time you're there, you're riding the escalator, grab the handle, right? Grab the banister of the escalator with both hands and pull it back as fast as you can, as hard as you can. Right? You're going to cause it to slip, right? And it will move. The entire thing will move with the velocity that you're moving it with, right? And it has the added bonus of making everybody else who's above that point on the escalator being really creeped out because their hands are shifted back. So what we used to do when I was a kid. Anyway, but that's the point, right? If you can take any part of that belt and you can pull it, the entire belt's going to move with that speed at that instant, right? So that's kind of, I guess that's the point of these two problems. One of the points, right, is that if we see a belt drive system or a cable drive system, you can assume that at the instant shown, every point on that cable or that belt has to have the same velocity and acceleration. Any other questions? Let's introduce general plane motion, and we'll probably leave it there for today after we get through the introduction. I don't think we're going to have time to do a problem. But we'll. All right, so what is general plane motion? So as a woman approaches to release the bowling ball, her arm has linear velocity and acceleration from both translation as well as the rotation of her arm about her shoulder. It's not just women, this happens for men too when you go bowling. So don't feel like you're left out, guys. What is general plane motion? General plane motion is the study of any system that is both rotating and translating simultaneously. For example, let's take this wheel. This wheel will roll, right? But point A also moves translationally, right? So how your car works, right? The wheels move, but you move forward as well, right? So the wheels are rotating, but the wheels are also simultaneously, because of the rotation, moving forward, right? So the way that we can kind of discuss these problems when we're talking about general plane motion is we're going to break it down. We're going to break it down into just the translation of a specific point on our rigid body. And then we're going to assume that that point remains fixed in space, and we're going to rotate everything around it. So in the case of the wheel, right, we move the wheel standing straight up. We're going to slide it from A1 to A2, right? Then A2 is going to stay fixed in space, and we're going to rotate it until we get B1 prime to the end position B2. Now, obviously, this isn't how it works in real life, right? Things happen simultaneously, but the end effect is the same, right? Because we are now at A2 and B2, right? So we can break this down into a translation and then a pure rotation. So it's neither a translation nor a rotation, but it is both, right? And the displacement of a particle AB to A2, B2 can be divided into a translation and a rotation, okay? To discuss this, we have to talk about relative and absolute velocity in planar motion. All right, so it's general plane motion, so it's going to be a two-dimensional problem because it's in plane, right? It's planar. So if we start with our potato here, right? So we've got our potato. I've got some point A and some point B, and it turns out that A and B have different velocities. Right? Why? Because they're rotating. Right? They're rotating. But I can change this into a translation, and in this case, I picked point A. Maybe I know the velocity of point A, right? Maybe I know it. Also, it looks pretty straight, so I mean, that's always a positive, right? So I'm going to assume that both of these particles, both of these points translate upward with the velocity of A. Then I add to this the rotation about A. And notice, in order to define the velocity now, I need to use the velocity of B with respect to A. Okay, so any plane motion can be replaced by translation of an arbitrary reference point and a simultaneous rotation about that point. The total velocity of B is broken down into VA plus V of B with respect to A. This is not a new equation, right? We've seen this before when we talked about relative velocity. But it turns out that we can define V of B with respect to our relative velocity as R times omega. This is just R times omega, right? Okay. So the total velocity of point B is equal to the velocity of point A plus omega cross RB with respect to A. Okay. And in planar motion, this is just omega times RB with respect to A. So the distance between these two. Okay. Let's look at this slider. Same general idea here, right? So assume that the velocity VA of this end of the slider is known. Typically, if you know the velocity, that's the one you should pick, right? I know this. I want to determine the velocity of B, this end here, right? And I want to do it in terms of the angular velocity, VA, L, and theta. All right, so I know the direction of VB and VB with respect to A. I can complete my velocity diagram. Now, the book really likes to do these velocity triangle diagrams. If they work for you, then great, but this is not the way that my brain works. I prefer to do it not graphically, but this will work too, right? Because we know that if we have VA and VB, then V of B with respect to A is how we get to point B from point A, right? Is the velocity of point B as if I was standing on point A, okay? The velocity of B with respect to A. If you have this triangle, then you can do the trig to come up with relationships between VB and VA. Right? And then we can come up, we can use these relationships then in similar triangles to come up with omega and L, right? What happens if we do it the other way and we know point B and we want to find velocity at point A? Guess what? It's the same thing. You'll end up with the same thing, right? The angular velocity of omega of the rod in its rotation about B is the same as its rotation about A. Angular velocity is not dependent on the choice of reference point. Right? These are the same vector, they're just in different directions. Right? So the omega is going to be the same. Omega is going to be the same. It's a repeat, isn't it? Yeah. It's a repeat. It's so good we wanted to do it twice, right? All right, this is also a repeat. Great. We have time to do this one. Let's see. We got like 10 minutes. I don't think it's value added to start this problem right now. So we'll end for the day. Okay. Startup class with this problem. Next time, it's a gear inside a gear inside a gear, hence gearception. I know. a lot today. We've gone through quite a bit, right? Next class we'll do a few problems. You guys will get a shot to do a couple of these, right? I'll do one, you do one. You're gonna see that I know that these seem intimidating up front, but we just need to break them down into parts that we can do. If we can get a handle on the kinematics of rigid bodies, then this stuff, spoiler alert, right? This stuff is going to come back up again when we talk about Newton's second law, because now that we have rotations as well, there's more equations that we can have, which means there's more unknowns. Right? Means there's more unknowns. You guys fill that out, then you can